Today is Professor Nachbin from IMPA, Brazil, and he will talk about the flow in water.
Well, thank you very much. Thank you all for being here. It's actually a great pleasure to be here at the Newton Institute, be here with this audience, which mixes, as was announced before, from analysts to applied people. And I want to share with you some research actually on this problem, which I'm calling capturing the flow beneath water waves, which has three parts. So first of all, let me put this slide here. I know I'm at the Newton Institute, not at the Schrödinger Institute, but this is just so I can officially, in public, thank Adrian Constantine, whom I met at the Schrödinger Institute 2011, and that's when I basically got started on this problem, and Adrian has been very friendly and generous over the years, telling me things of what people have been studying in analysis and so on, and things to look in computation. So Adrian, it's really been a pleasure interacting with you, and I want to do this thank you in public because it's really been great fun and great pleasure. Okay, so let me get started with work. So as I said, there's three parts. The first two parts are more closely related, and it's as the work started talking to Adrian back ago. So part one is on irrotational waves, then I'll move on to rotational waves, and this is a numerical study. So we were trying to, with a former graduate student, Roberto, trying to capture things that Adrian collaborators and other people's in papers were seeing. So first we start with closed orbits. So I'll show you two slightly different numerical modeling for these two problems. So in closed orbits, basically guided by what you would see in this paper of Walter Strauss with Adrian, we start then modeling this, and it's very simple to just write what one needs to do if one needs to track particle trajectories underneath a wave. Basically, you have to solve this very simple looking, but not so simple, dynamical system, right? So basically, we need to compute the vector field as accurate as we can to be able to see what the particles are doing as a steady traveling wave passes by. And we have incompressible irrotational flow. That's how we're going to start. We're going to add a current. Later on, we'll add constant vorticity. And we want to compute this potential as best as we can, so we get the vector field as best as we can. And we'll do this via potential theory. Okay. So these are the types of orbits that are sort of indicated in the Constantine-Strauss paper. And actually, when we do the numerics, we're able to find, these are our target first was to get these closed orbits. And actually, we also found these orbits here, which are basically these loops when sort of the loop goes to zero, right? Just a perfect balance between trying to loop and the wave brings back the particle in the other direction. So kappa is the current, and basically the closed orbit is when you have this adverse current that basically closes what would be the Stokes drift. So these are basically the qualitative results, and let's see if the numerics we can get this. In particular, as I said, our target was the closed orbit. So how do we do the numerical modeling for this problem? So basically classical ingredients plus one ingredient that I had never tried, and I thought it was good, but it's also nothing special. So here goes. We have potential theory, Laplace equation, and Neumann condition of flat bottom. And we have our free surface conditions. And basically, we're going to try to do a boundary integral formulation, which basically is Green's identity, or more specifically, Green's third identity, with a given Green's function. Okay? So we basically, since we have periodic waves, we have this periodic cell. And let's try to be as economical, if I may call it that way, as we can for the computations. And that's where something I had never tried, and it was quite nice to see it working very well here, is we choose this periodic function that I saw it in a talk by Patrick Guidotti some years ago. And with this periodic function, Green's function, we basically erase this side and this side of the periodic cell. With the method of images, we erase the bottom, and the computation becomes then literally only using the free surface. Basically, you write the vector field down at any point in the bottom, say, without getting wet, right? Without diving. So the other good aspect of this is that by erasing all this and having the computation over with periodic functions over this curve here, we have this expression here that is not so nice looking just because of the parametrization, but we have an integrand of a smooth integrand, right? Because the Green's function, the point is down in the bottom, in the middle of the bulk of the fluid. We have a smooth integrand, and trapezoidal rule is spectrally accurate. So we have a highly accurate method in a very, very simple way, right? So that means spectrally accurate means if you have a function that's analytic and its Fourier spectrum decays exponentially, the arrow decays exponentially. If it's band limited, it's exact up to round of error. So that's very good. So this is what the trapezoid rule is doing for us, very simple. And all we have to do is compute the potential and its derivatives. Basically, we need its derivatives here, and basically have the vector field for this ODE, and say use the standard classical Runge-Kutta method. And I'll show you the orbits, and I'll show you what we get. Okay, so this is for the irrotational case, and here we are. This is in a fixed frame, laboratory frame. This is in a moving frame. Here is the closed orbit up to 10 to the minus 16. So there's no drift. We see drift where you're supposed to see drift. It's very nice to see that these points are along a streamline, as mentioned in the paper by Constantine and Strauss. And I think, and Adrian or somebody else might correct me if I'm wrong, I think, of course, it's known it's over a streamline, but I think given a wave profile and so on, one cannot predict exactly which streamline, where is it? Is that correct? So anyway, so it's very sharply on the streamline, the points following here. Okay. Then here it's with topography. Unfortunately, this video is not very clear due to the resolution. So I've been working most of my career with waves over topography and waves over sharp topography, where I've used the Schwarzkopf mapping to map it onto a uniform strip. So this is a preliminary, just starting playing with this. So we have these barriers. We have a point here, a point there. This is the orbit for the yellow one. This is the orbit for the red one. This is where the barriers are close together. This is basically 100 times smaller. And this is just testing the boundary integral formulation. And again, it's not very clear, but again, we were able to erase the sides and the bottom because before we do the computations, we use the Schwarzkopf mapping to map this, or to map this domain onto a uniform strip. We do that using a very nice MATLAB toolbox by Toby Driscoll. Very good actually to teach complex variables and to draw all these level curves in xi and zeta, right? The Cartesian coordinates over there in the canonical domain that becomes orthogonal curvilinear coordinates in the physical domain, and the Laplacian remains invariant. And basically, so we're doing these computations here using the same scenario as before, erasing sides and bottom by basically mapping and so on. Okay, so now this is for irrotational waves. Now let's go to waves with vorticity. And the things we were looking for, more or less in this order that we started looking for, was stagnation points, phase space structure, and pressure anomalies. Okay, so the formulation ended up being, we started doing similar to as I showed you before, but it started being at the end a little different, and actually probably better in terms of accuracy of finding some of these points. So this is how it goes. Well, first, many of you know, for this problem in particular with constant vorticity, we can sort of decompose the problem and solve it for the harmonic part. So that's therefore we get a free ride and all this boundary integral potential theory formulation. This is constant vorticity. We played with different profiles, but basically I'm going to show you results for this one. And how do we do the formulation, the numerical formulation for this part, the harmonic part of the flow? We do it, as I told you, slightly different than in the previous example. Well, let's go by parts then. So here's the formulation of the problem. where now one have to just keep in mind that psi tilde is not the stream function. It is basically the harmonic conjugate of the harmonic part of the flow. Okay? So let it sit there. And at one point we're going to use Cauchy-Riemann equations, whatever, to compute one guy from the other, right? But it's not the stream function. When I show you a plot of the streamlines and so on, that's of the stream function, not this guy here. So B is the Bernoulli constant, and eventually we're going to use these guys for the pressure. You're going to see an expression here for the pressure. And okay, so let's keep on going. We basically put ourselves into the moving frame to start with, and use the expression for the pressure that we're eventually going to compute it using these variables. And we're going to do one more change of variables, which is we're going to do a conformal map now, which is not, there's no topography. It's going to do a conformal map that will flatten the free surface, and it's a little bit along the lines of some papers of Adrian with Eugene, at least that I find in this group, which started using things similar along these lines. So numerically, how do we do? So we kind of, as the way I'm going to explain it here, it looks a little bit backwards, but that's the way we built up the strategy. So we have this problem, right, in a moving frame. We don't have the wave elevation. Actually, I should mention, but I didn't want to spend too much time. The previous problem, we started using as our wave profile approximations of like Fenton's approximation and so on. Here, we have to cook it up through a sort of a continuation method, and I'll show you just in a second how we do it. So let's think of the problem in this way. This is the problem I have in the physical domain, and this is the problem that I have in my canonical domain, where we have flattened out the free surface. Okay, one of our choices, right, that's not the choice, one of our choices, is that we choose that the problem is lambda periodic. It's going to end up in the numerics being, I think, 2 pi periodic in both domains. That means that D, the depth here, has to be calculated according to your wave elevation, right? It's very high, so things are conformal and so on, right? Some people sometimes keep both depths equal to 1, whatever, and then it's the wavelength that changes from one domain to the other. No big deal. Okay, so here, now, so that, there's going to be a slightly busier slides, but I'll try to communicate without having you to read everything, but it's a way easier for me to tell the story. So in telling the story, here is like this. Suppose, right, so now let's suppose we know the wave elevation, which we don't, eta in the physical domain, and we map it over here. So we'll call this function here capital Y of psi, right? We don't know it, but suppose we do. This is a Dirichlet condition for this very simple harmonic problem, right? Laplace problem in a strip with a Neumann condition over a flat bottom and this Dirichlet condition here on the top. So we can write Fourier integrals and so on. That's going to happen in just a second. We yet don't know what this guy is, but in what will follow, this bold Y will appear on and on and on, and everybody's going to be sort of computed out of this guy. Okay, I'll prefer to repeat myself. Sorry if I bore you, but I'll say this again. And more or less the numerics strategy follows a bit what had been done by Woo-Young Choi and Paul Milevsky that collaborated in this part of the research had done before. And as I said, from the theoretical point of view, it's a little bit along the lines of what Adrian Constantine and Eugene Varvaruka did, and also similar to a recent Acta Mathematica paper of theirs with Strauss. Okay, so trying to make the story short, we have the Bernoullian kinematic conditions in the moving frame, right, this capital X. Now, I'm skipping some details with just boring details. Now we rewrite this derivative chain. We'll rewrite it in the canonical variables, right? We sort of mix these two equations together, and we get this long equation in terms of the capital Y that I mentioned to you. Okay, and I'm going to highlight something now, which is this. Not only at this stage we don't know Y yet, which is our wave elevation in either domain, but also therefore I don't know also the depth in the canonical domain, I don't know the Bernoulli constant, and I don't know the speed of my wave. Okay, I have one equation and 3 unknowns here. Yes?
So is it canonical to you always means for a one coordinate?
Yeah, Yeah.
You
That's what I mean.
see this.
Yeah. So, for example, let me put it this way. Right here.
To clarify.
Yeah. Here, find everything. So this holomorphic coordinates related to conformal mapping. Okay. But that's what the x and the y are, and that's. But here, everything is smooth, just flattening out the free surface, and you have the holomorphic coordinates. Yes. Okay. All right. So I was here. Okay. So that's now this long expression. I'm just going to lump it all together and call it g of something equal to of these somethings equal to 0. Here it is, and I'm going to complete the system that we're going to try solving the Newton-like method with other information relevant to the problem, right? Things that we like to ask. And the things we like to ask here are, well, this expression, we're going to prescribe a wave height as big as we can. We're going to say it's mean 0, and the depth comes out of this wave that comes out, the depth in the canonical domain. So basically solving this, eventually we get all these guys. We get the wave speed too, if we can do it, right? If the code runs to the point we want, a sort of continuation-like method. Sometimes we cannot go as far as we want. Sometimes we go, I'll show you some computations. We go increasing vorticity. In other situations, we go increasing steepness. Usually we can increase vorticity more than steepness, and so on. And so say after we get the capital Y, which is basically our wave elevation in the canonical domain, we can then start getting the other variables. So there we get basically this capital X because of Cauchy-Riemann equations. So in the middle comes this sort of Hilbert transform on the strip. These are all Fourier integrals. And I think in the next slide, yeah. So basically we solved somehow the problem for the map in the sense that, okay, now we know what this guy looks like. All the other guys will follow up. So this is how the Y looks like. We get the X and so on. We can then go to, if you get the potential and the harmonic part in its associated conjugate harmonic psi. I think I have it in the next slide. Yes. Here, all depending on this Y. It's just cranking the wheel, putting all these guys one depending on the other. And then we're ready, with these guys, we're ready to compute the orbits of the particles in the bulk of the fluid. And we can do these in different ways. We can do this a little bit along the lines as I did before, with sort of a Green's identity, right? And basically doing this the chain rule. But actually, for this case, we can just compute these guys also and do many of the calculations in the canonical domain and then mapping the results to the physical domain, right? Basically, here, knowing what, once we have these expressions here all depending on Y and so on, we can get anything we want here and compute actually which is the point where the speed is 0 and so on, and mapping and going to the physical domain, which things won't change, and doing all these things, then mapping the results, doing the animations all here. So this is the general sort of strategy for setting up the problem. Okay, let's see if there's anything I'm missing. No, so the orbits, all right, so we can use it through the Green's identity as before. If you like it for any reason, well, I want to compute things just from the free surface in the physical domain or in the canonical domains, just the Green's, I said Green's function, I want to say Green's theorem, right, third identity. Or you can just in the canonical domain go downstairs in the bulk, compute things, and map it over. Okay, so some earlier results. So some earlier results, famous papers well known to the community. Of course, this one, which is maybe the starting point of many things, at least suggesting things, the paper by Teles da Silva and Peregrine, and then the paper by Cohen-Strauss and Vass and Olvesa, many others. I know there are many people around here also in this room doing computations, but I'm just going to cite these three. And here are some pictures, for example, from Teles da Silva and Peregrine. Teles da Silva, actually, Fernando was Brazilian, and I actually met him, unfortunately, passed away at an early age, was a student of Peregrine at Bristol. So in their paper, they indicate, right, these are these streamlines. There's a Cauchy type integral formulation for the numerics. And the points, these integration marks are, I put it that they just do this qualitative rendering of the streamlines, and also this qualitative rendering of the pressure, indicating that there's a point here where the pressure can become lower than the atmospheric pressure, which is basically constant over here. And they mention things which are actually good for intuition, as that they say that if these large waves are stationary, then there's a thin sheet of high-speed water passing over this eddy. And for my sort of acquired intuition from doing the computations, reading the paper, talking to it, and so on, this to me is a bit like, as you will see in the pressure anomalies, I think follows, at least from my perspective, you might have a better intuition than me, is that it's almost in the stationary framework. This is acting a bit like a hydrofoil, right, which this high-speed jet will lower the pressure here and will increase the pressure here, and therefore you're going to get very high pressures. In particular, one of the pressure anomalies is getting that the maximum pressure at the bottom in some situations is going to be below the trough and not below the crust, right? So you have this stagnation point here, which with our method we can compute exactly the point, right? That's a place where the flow will decelerate a lot. It's a little bit like a compression. The pressure becomes high. And over here, the pressure is lowered by this very high-speed jet on top of the fluid. Coe and Strauss they have two papers, at least that I'm aware of, with nice computations using a continuation method, and they do it through the de Broglie-Jacotin transformation. And of course, they cannot go to the point where these two guys meet, but can go very close, indicating that you have a point where the particle is flowing with the wave speed. No, not a question. Okay. And then we have the paper by Vassan and Oliveras exploring the very nice method of non-local formulation by Ablovitz, Focus, and Muslimani. And they also indicate the same structure. They indicate the pressure anomalies, somehow indicating that it could be, it's not quite clear that it is indeed at the saddle point, this other critical point. But they already say the maximum of pressure splits away from the crest, and so these are three recent papers. There are of course more papers and efforts in this direction, which is good. And let me show you some of our results now with the method. Okay, no, before then there's this other one, which is a more analytical paper by two of the authors are here. The third one I think will be arriving soon, right? And basically mentioning about the critical layers and the structure that in the paper there's a picture of like that of the recirculation zone too. So this is from the analysis point of view. Okay, our results. So as I mentioned, we're trying to get the precise location of the three stagnation points in the eddies. We're going to show some videos that Roberto, the former student, did, and I like them very much. It's really a pleasure to see them over and over. I know I'm already trying to capture your heart, but I like seeing it. It's really nice to see how if you look at one frame, it's a mess. If you look at another one, it's really organized. It's very nice. And the pressure anomalies and so on. Okay, so let me get started. So this is then our, as I mentioned, we're basically putting the period to be 2 pi. We get the depth, we get everything. We cook up through the continuation method our wave profile. And then here's the stream function. This is the harmonic conjugate of the other one. And we will get structures like this. Okay, so here basically is the wave profile that was cooked up through the continuation method. In this, for this value of the vorticity, we have 3 stagnation points, this center and these 2 saddles. And I think the next slide that I'll show you is basically an animation through vorticity. So, right, when you animate something is in time, this is an animation in vorticity. So as vorticity grows, so right, increases, that's a better word, as vorticity increases, you will see the animation of these stagnation points, and we'll basically see how they come in, branch out, and so I think the animation will speak for itself, and I think it's, I was very pleased to see this when I saw it for the first time. So this is just indication of just what I said to the boundary interference, and oops, and just before, this is just a picture of then basically when the recirculation zone is basically sitting at the bottom, and then you increase the vorticity a little bit, it goes up, and you get these cat eyes like structure. Okay, now it's the animation. So this is animated in vorticity. So you see one point appearing, one stagnation point appearing through the bottom. It breaks into 3. It starts spreading, and maybe I think a good way to do it is now do it manually. Is that right? So here, basically, we have 3 stagnation points. 3 stagnation points. 3, 1, and at the end, when it hits the boundary of the periodic cell, we basically say that we have 2 stagnation points because the 2 saddles are basically the 1, right? So this is then we have our phase space streamlines and this animation with vorticity with a fixed steepness. Now here the steepness is being varied and the vorticity is kept fixed, and we see a little bit the same kind of bifurcation pattern. It's just that the method we're using breaks, I mean, doesn't go any further in terms of steepness. We don't get a recirculation zone bigger than this, and it was also not our main object of interest, so we stopped here and continue with other things. But we see again the similar qualitative picture of one point appearing, breaking to 3, and opening, and so on. Okay, so this is an animation in steepness. We cook up a wave for a given height and so on, keep the vorticity fixed, and then start increasing the steepness. Every time we change the steepness, we have to find all the initial data and so on. Okay, what's next? This is what's next. Fixed frame and moving frame. And I think the picture will speak by itself. Let me take a drink of water. Right? No wonder, I mean, theory analysis has to be done in this frame. This is a mess, right? I mean, but it's basically the same particles, right? So here's a stagnation point. Here's a stagnation point because it's moving with the same speed of the wave, and it's very good actually. Roberto is able to calculate this in a very precise way, so it really is not even oscillating. Moving in the beginning would oscillate a little bit. We'll calibrate things, and here we see the streamlines being drawn by the particle. It's not the phase sort of diagram, and it's very nice to see also along these blue lines, these guys are moving much faster, which is the fast jet, as Peregrine said, above the recirculation zone, right, which will eventually diminish the pressure up here. I'm gonna show you a pressure picture in just a second. Maybe the next one I don't have all sort of memorized. So this is one of the videos that I told you that I like very much seeing over and over because this is a mess and this is very, very nice. Okay, so this is an animation for the pressure as we increase vorticity. These are what we saw, the streamlines. This is the pressure. So I'll go back there and do manually too because it's good. So this is the pressure level curves. Those are the ones we already saw before, the stagnations point coming in and out. So let me sort of go back here. So nothing's happening. So maximum pressure beneath the crest, no surprise. And as we go, increasing the parameter, changing a little bit, increase the parameter. Okay, we have already 2 saddle points appearing, and that's already made up splitting of the pressure maximum along the boundary, bottom, sorry, it's the bottom, but it's the bottom, and off it goes, and then suddenly, let me see, yeah, here there's already a maximum of the contour graphs of MATLAB didn't pick it up, but here we already have this point of minimum pressure up here somehow over this quote unquote, that's how I was calling with my colleagues, hydrofoil-like structure, right? So at least the way my intuition kind of works or was acquired for this problem. Okay. All right. So these are the two publications. First is for the rotational waves, closed orbits, and so on. And this is for the one with stagnation points and all these results. There's a little bit of the, it wasn't our goal either, but overhanging type profiles. We just got the onset of those overhanging profiles in some parameter regime, so we display some of those, but it was not our main goal. And this is really future interest. I mean, we've done, as I showed you, a little bit on the inclusion of topography, which is something I've had some experience. I would like to maybe do more. And, you know, there's other things that numerically, which we would like to try, and I know that people already have the interest in that. So the stability of the traveling waves, shear layers, more different vorticity distributions. Anyway, things to be looked at from this computational point of view, and so on. Okay, so now actually I have more than I need in terms of time. Maybe I'm speaking too fast, getting excited, so please also interrupt me and ask questions as I go along. And now there's the third part in terms of capturing the flow beneath water waves, which is different from this, but I wanted to make sure I could share this with this type of audience that we have here. Okay. So the third part is this problem. Is a problem with a former student, Davi Andrade, who's now fortunately a postdoc at IMPA, because Davi changed after his qualifying exam from a more pure analysis background and then started to learn numerical PDEs and fluid dynamics on the fly and did very well. And our goal was to try to construct numerically this 3D Dirichlet-to-Neumann operator over a variable depth. So I'll tell you a little bit how this animation is being done, but this animation, there's a circular mound here in the bottom, and you see that the wave starts moving slower, and the computation is just 2D using this pseudo-differential operator, which we worked on over recent years and just submitted a paper recently. So the computation is in 2D. This is the refraction by a submerged mound, and let's study this object numerically. So what is here at the stage is basically, in this case, is a linear wave, so it's almost a bit not allowed in this conference, but I hope Adrian doesn't complain. That's linear waves. Yes?
How was the initial conditions constructed? What is it? Is it a solid dot, or is it?
Here?
Yeah, in animation before.
Oh, in animation. No, okay, this is for this case, it's linear wave, so it's a plane wave with a Gaussian profile. Okay? So with a Gaussian profile, and I think for this case, in some cases, Gaussian profile for the potential, and you know the corresponding profile for the wave elevation. So okay, so this is a linear problem.
Just another question. Have you
Sure.
ever had a scheme for soliton propagation to see if really you get a stationary evolution of your soliton?
Say the beginning of the question.
Have you also tried to reproduce
Well,
shallow water solitons just to validate your model?
well, this one I can't because it's a linear.
Well, of course.
Right. So but one thing. Well, let me anticipate a little bit. One thing we're doing. So we have this for linear 3D waves. Davi also did recently. We're finishing writing up, which I'll mention at the end. But since your question is, we did basically. I had done before basically a Boussinesque system for just in 2D water waves. So it's a 1D Boussinesque system for highly variable topography. Because basically using theory from my PhD advisor, George Papanicol, of waves in random medium. So I would have to model random bottom and so on and so on. And I got things going using conformal mapping. I'm in 2D, so piece of cake, right? So map it, and I got this Boussinesque equation. And then eventually we did also solitary waves numerically over random topography. And the solitary wave profile we used came from the second order Boussinesque equation, meaning I was working with a system, but if you reduce the system to a second order PDE, you get the solitary wave there, you bring it over to the system, which is not an exact traveling wave, but for numerics we do it over a flat bottom. For the time interval we're looking at, it looks like a traveling wave and so on, right? So that answers your question partially, right, in that direction. And then we do the wave interacting with the bottom. Here we haven't done that yet. And okay, so the other part I haven't said, let me keep it for the end because it was prepared for the end. So I'll say it anyway. Okay, so I won't forget. So we have the linear problem. And now, right, so it's linear potential theory. We have we're in 3D. This is the Neumann condition at the bottom. So the bottom is variable. We have the linear free surface conditions. This is the trace of the potential at the free surface. And we basically want to work only with this guy. Namely, we want to rewrite the problem in this ODE-looking kind of fashion, right, where we have this non-local operator, this Dirichlet-to-Neumann operator, in the presence of the topography, and this basically pseudo-differential equation. Will it capture well the varying topography as I know? Basically, even though I'm announcing it to be 3D, the first simulations I'll show you are 2D, because with 2D I can use, say, my conformal mapping strategy as a benchmark, because I know it's very accurate and so on. Okay, so if I had a flat bottom, this is very trivial to do with FFTs, because the Dirichlet-to-Neumann map basically can, formally speaking, just very quickly doing it like this. This is the Fourier transform of my Dirichlet data. Right, I'm omitting time here. That's not a big deal, just for keeping things simple. And this is basically the harmonic extension of this Fourier mode on the free surface. We get then the Dirichlet-to-Neumann map, and basically this is the symbol of the operator and so on. So basically do an FFT, multiply by the symbol, and you have basically the ODE-like structure along the free surface. Now when you go to a variable bottom, right, the ansatz is a little bit like this. You add this term, we need to know what is this sort of Fourier coefficient here, and that's where the problem comes in. This follows more or less the structure. What we're doing follows more or less 3 papers that are very relevant and interesting related to. I hope it's not that small, and actually the resolution is not very good, so for people in the back I'll read. It's basically, there's a paper by Walter Craig, Philippe Guillen, Nichols, and Sulem, 2005, which they basically write this and prove that the operator, one of the operators can be inverted and so on, and they write this as in operator notation, meaning they actually don't have a Fourier series. We're doing numerics in the periodic domain, so you have a Fourier integral, and then these guys disappear, and here say instead of kz you have d and so on, right? That's the operator notation for these guys, and you invert it and prove things. But then they even doing the numerics is another story. And then there's, as I mentioned, the paper by Avlovitz, Focus, and Muslimani. There's a non-local formulation that is more or less along these lines. And there's, I think, a very interesting paper by John Wilkening and Vishai Vasan, 2015, where the title is Comparison of 5 Methods for Computing the Dirichlet-to-Neumann Operator for Water Wave Problems, and where they show that this is numerically difficult. There's some ill conditioning, and basically the way we're doing this setup here is basically what they call here the AFM star. So it's a bit like an adjoint of the Avlovitz, Focus, Muslimani formulation. So okay, so take this as an ansatz for our potential in a variable medium. So this guy comes in. If the medium was flat, it's basically this is what we had before. Now after plugging in the conditions and so on, one gets a relation like this, and this is basically we have to invert a matrix and so on. And if we solve this problem, we compute this x and we plug it in here, differentiate and so on, and we get the Dirichlet-to-Neumann operator with this matrix decomposition, say, in 3D in a numerical fashion. So without showing all the details, right, we get this is how we're going to do it. After we have these coefficients, it's basically an FFT. As Wilkening and Bassan mentioned, this is the guy that gives you a bit of a headache, and you can see also, right, as K increases the high frequencies, this guy grows a lot. But then one way we got around this, which is quite simple, and a fancy way of saying it is that, well, look, if this is the topographic term of this Dirichlet-to-Neumann map, we know that short waves don't feel the bottom, right? So we basically pick, okay, particles are doing, with a very simple linear approximation, are doing orbits of say 10 to the minus 3 near the peaks of our mountains, those modes are out of the dynamics, right? So basically we don't use them. And by doing that, we were able to succeed and do the computations I showed you. Without doing it, you eventually get noise into the numerics, okay? So basically, in a nutshell, this is our 3D Dirichlet-to-Neumann operator, where this guy comes out of solving a system from, as I showed before. Okay, first step of benchmarking, which goes back to the conformal mapping. I know how to do, been doing this for a while, abrupt mountains with corners and so on. The conformal Schwarz-Christoffel is built for that, for polygonal shaped domains. This is 2D. If I do the conformal map, I do my Dirichlet-to-Neumann in the canonical domain, which is the trivial one. It's flat, it's the hyperbolic tangent symbol, blah, blah, blah. Come back and so on. It's very precise. And here we're comparing a snapshot of the solution of the Dirichlet-to-Neumann strategy without the conformal mapping, which is this curve. And some points, we didn't put all of them, or else would be populated with crosses here. Some points of the conformal mapping one basically falling on top, and the error is small. Okay, now let me show you some dynamics, some animations for the wave with the Dirichlet-to-Neumann computation. It's still in 2D, and at the end I'll end, I have some time, with a 3D simulation. And I'm going to start with, I'm going to do a mean zero periodic bottom, which basically will bring us to Bragg resonance kind of scenario. And then I'll put a periodic bottom that's rapidly varying. That takes us to a paper by Rosales and Papanicolaou, where you see basically a homogenization effect. That is, the wave doesn't reflect over this periodic bottom, but it changes speed. And you will see that the Dirichlet-to-Neumann, this Dirichlet-to-Neumann operator, that here, the way I'm doing, we never see, quote unquote, its face, right? Because it's this matrix here and there, but it's there. It's what the operator is doing. Okay, so let's go to so this is the order 1 guy. So you see these waves are basically twice this. So it's the Bragg resonance. This is still Bragg. More or less, these guys are still double this guy. So it's kind of working. Now I'm going to put a rapidly varying topography. Wasn't clear that this non-local formulation would handle it. This mean zero rapidly varying topography. So note here, because in the next slide we won't be able to see it. Here, this bottom is mean zero, clearly seen. Here it's mean zero. In the next one, it's also going to be mean zero, but it's going to be rapidly varying. And here it is. Here is the wave. There's a reflection from the step. There's no more reflection. And in this region, there's an effective speed and an effective dispersion due to the rapidly varying periodic feature of the bottom. And this is something you would see in this paper by Rosales and Papanicolaou. And here, what this graph is showing is that the red wave is what would have happened for the flat bottom. The green wave is what would have happened for the envelope, which would be this step. And the blue is what we're seeing here above. So indeed, you have an intermediate speed. I mean, the bottom is mean zero, so the average speed is not 1. It's something in between. And it's a little bit in the spirit of composite materials. You have a mixture, right? And the conductivity is smaller than 1, right? It would be 1 if it's the flat bottom. The inclusions, which is the bottom variations, are mean zero, but the speed is not 1. So there's an effect. But it homogenizes. There's no reflection whatsoever. And it was nice to see that this Dirichlet-to-Neumann formulation captured this in an appropriate way. Not complaining that in any way that the derivatives of the topography are quite high, right? Because it's rapidly varying. And I think my last simulation, which is also I think interesting, is 3D. So what we'll see in the next animation is this. I have a plane wave that's going to encounter a specially designed circular mound, different from the first one. Okay? So the initial condition is a little bit, as I said, a plane wave with a Gaussian profile, but the mound is called the Lunenburg lens, comes a little bit from optics, that basically focuses the wave energy at the back of the mound. And these rays here, David sort of traced them by doing like a ray tracing and geometric optics approximation of this dispersive model, showing where the rays would be. And actually, and this is a contour plot of in MATLAB of the wave heights, which we see starting to bend. So it's orthogonal to the rays. That's good news. And it will eventually sort of focus here, generating a big splash. Again, this is a linear model, and the Lunenburg lens works. So showing this 3D sort of dynamics with this refraction pattern. And this is done by using the Dirichlet-to-Neumann map as indicated. So let me show you, I think the next one is the animation. Yes, so here it comes. Somehow here there's this submerged mound that has to be very well fine-tuned for it to reflect and to focus and do this splash in the middle, and there it goes. So this point is basically this point here with a very good accuracy. The computation is just doing that on its own. Okay, so basically my conclusions on part 3 is that we have explored. So this is, you can find those who are interested at Archive. We recently submitted this paper. And so the conclusions are we explored with this 3D Dirichlet-to-Neumann operator with non-trivial topographies, in particular looking rapidly varying topographies or these phenomena as I described to you. So there's this underlying, right, that I said we cannot sort of see its face, quote unquote, but there's this underlying variable coefficient pseudo-differential operator, variable coefficient in the sense the wave speed changes, the medium properties change from point to point, and it captured including fine features of the topography, which is that homogenization-like effect, which was nice to see, and current and future work, and that's the thing I knew I was not going to forget to say, is this 2D Boussinesq model, which is the following. Now, this is a weakly nonlinear, weakly dispersive model, which we already started comparing with this linear, fully dispersive model. But the Boussinesq model, what we've done is something, an old idea finally with David we did is this. I was thinking, well, so I can do oblique incidence or whatever, to use conformal mapping in a 3D scenario, even though we know that the Laplace equation is not invariant anymore. The Jacobian, right, if I do the conformal map in xz, and the Jacobian is going to hit the yy derivative of the Jacobian, of the Laplacian, and it's not going to be invariant. But can we sort of still survive, do something, cook up a reduced model along the lines I did with my 1D Boussinesq system to have a model that can deal with, you know, sharp or whatever highly variable ridges in one direction, even though the dynamics is not going to be 1D, because you can just put a mound and abandon it, put incidence, oblique incidence, and so on. And we're having success with this. We're writing that up. So in terms of current and future work, one is this 2D Boussinesq model that I described to you, which is basically 3D potential theory with conformal map. We're comparing with this method, and we plan to, in particular with the 2D Boussinesq model, to revisit something that I did some time ago, and again, exploring ideas from acoustic waves that George Papanikolaou was doing with collaborators, which is waves in random medium, and in particular when you have a random medium, if you're doing like a hyperbolic system and you're throwing a wave over a randomly varying medium, layered randomly varying medium, you observe something that's very nice. It's apparent, you have an apparent diffusion in your solution if you're in the right scale, if it's rapidly varying. So it looks your solution has diffusion even though there isn't. And then if you record the reflection, for example in the 1D case, and you send it back in a time reversal fashion, you can refocus the wave. Actually, you can reconstruct your initial data if you're doing it 1D, and there's other things you can do in high dimension. So this is one thing now with the Boussinesq system. So it would be nice because in acoustics they have like locally layered medium, and you have the hyperbolic system. So this is basically weakly dispersive, weakly nonlinear. One can play with solitary waves now with oblique incidence, whatever, to be yet done, right? This is a little bit wishful thinking at this stage, but the model seems to be working. So this is the plan for the future, which is this, the tsunami waveform inversion and refocusing and so on. So thank you very much for your attention.
first set of work that you presented with the linear current.
Sorry, I couldn't hear you the first time.
In the first set of work you presented with the linear current, do you know what the group velocity is?
If I know what the group velocity is?
Did you work out the group velocity?
No, I don't think so. And why?
It may have implications for what are called stopping velocities.
Sorry, of the?
May have implications for what are called stopping velocities.
Okay, no. Okay, I see. No, we haven't explored. No. That's good. Thank you.
It may explain why you suddenly get a move into this cell structure.
Okay. No, didn't look at the group velocity. No.
I have a question. These overhanging waves, it's like an omega, or how do they?
No, it's not. Let's put it this way. I mean, it's far from what Van den Broek does, right? I mean, so let me see if I have a picture. For example, this one. No. A little bit like this. See. Not really, right? I mean, it's not even quite overhanging, right? It's getting stripped, so it's really, I don't even think, I'm not even sure. I said overhanging, that's a bit of my mistake. We have these very round shapes. I have to go back and see if Roberto ever got one that sort of around here was really overhanging. So it's a little bit like stretching too much, but it was not our main objective. So, but basically we got profiles like this. And let's see if my memory is sort of playing games on me. No, I think, Adrian, that's, yeah, so it's more like this, and then, see, this is a bit, I was mentioning, I think, with Eugene, right? This is a bit of a picture that Roberto took in the beach in Rio, inspired by a photograph of Peregrine and Teles da Silva, and basically that a profile a little bit like that one we showed would be something like this. The backwash from the sand, there's this sort of solid rotation here, a flow underneath it. Again, a bit of loose wishful thinking, right? Not really confirmed that this is. Oh, here's a little one, one a little bigger. Let me see what this guy is doing. It's just he's changing from deep to animation, phase deep, from short waves to deep waves. So this is going towards more like a solitary kind wave of regime.
The photo in Peregrine is also this back.
Yeah, the photograph in Peregrine and is this backwash, as they call it.
It's very similar. I thought that this is from.
It was very similar, yeah, but I mean, we couldn't. I mean, Roberto took a photograph that looked very much like theirs. Unfortunately, neither. I mean, we also didn't have to go to the trouble of asking permission to use a photograph, so but it looks very much like theirs, and it's inspired by theirs. Yes.
Maybe a comment. I mean, it's very fascinating what you do, and
Oh, thank you.
I'm thinking of the 3D. Of course, you can do that strongly nonlinear. I mean, with a variant of these operators, we have done that, and
You have done strongly nonlinear, but
Yeah.
and with topography,
Yes.
and like this Dirichlet-to-Neumann.
yes, of course.
Oh, I have to then become
Okay,
more.
I'll tell you.
Yes.
So one of the things I tested was like this dispersion when you have this randomly varying bottom topography, and I didn't get the diffusion. I just got the delay, and I was very puzzled about that. I can show you these equations.
You didn't get a diffusion?
It is never. I didn't get the diffusion. I got only the delay, the reduction in the wave speed. So I can.
Well, yeah, and
I can
so
show you
I
some
should be
results
aware.
of
Yeah, I
that.
should be. If you've done this, I should.
didn't. But my point is that you can do all this as long as you have, as long as it doesn't blow up in the spectrum. If it blows up, I mean, then you have to do something.
Yeah, that's the thing. That's the thing that sort of got lurking. You know, the thing that sort of for the topographic terms,
Yeah.
we use only a finite band, or else it will kill us in the computations. Yes,
So that is, of course, a severe restriction.
it is a restriction. Yeah, it is a restriction.
But I can show you.
Yeah, please, I have to see it because I want to know. Okay, I think I have to see it.
Further questions? The first part of your work, I know you were looking at the periodic solutions, and that's how it's structured. But did you see any
sensitivity to the initial condition. Like, in any particular regime, if you change, there was a significant change in the solution.
Well, if you change the of what you mentioned, the structure, for example, recirculation, all that.
No. In the first part, I think you were doing the transformation. Then your initial
First part of like the rotational waves. No, first part,
yes,
as I call it, right?
yeah. With your H is your basically initial condition.
Yeah.
So
No, if you change initial conditions, things change, right?
But is there a sensitivity, like, because it changed much? That's what I'm asking.
Well, it depends. For example, one thing I can tell is when we go from the steepness, which is basically changing the wave height and keeping the vorticity fixed, right? It changes. It changed quite. I think it changed slower than the vorticity one, and we hit a wall quicker than we did with a vorticity one, right? Because the waves get too steep and so on. So that's a little bit what I can say that I recall from these details from the computation.
Further questions? If there are no further questions, then let's thank the speaker.